In a universe stretched thin by eons, where stars have long faded and even atoms face their end, a single question remains: can intelligence find a way to outlast time itself? Imagine a universe countless eons from now, stripped of starlight and emptied of warmth. The galaxies have drifted apart into isolating silence, and even the fundamental particles that once danced in radiant complexity have begun to fade. Yet, in this boundless dark, a spark remains, a glimmer of intelligence that has adapted, persevered, and evolved to endure beyond time itself. This is the realm of Dyson's eternal intelligence, a vision where civilizations, pushed to the very edge of existence, defy the universe's slow decay, not merely surviving but flourishing. These minds stretch beyond the limits of entropy, grasping at eternity, refusing to be swallowed by the inevitable cold darkness. What would it take to persist in such an unforgiving cosmos, and what would life be like in a world where thought must outlast the stars themselves? Welcome to Science and Futurism with Isaac Arthur, and I am your aforementioned host, Isaac Arthur. And today, we're asked what it takes to survive in a dark era at the end of time, where even the most basic elements of matter itself might have decayed and entropy overridden all. This is not our first venture into civilizations at the end of time. It's a series we've been revisiting about once a year since our early installments, Black Hole Farming and Iron Stars, back in 2016 and 2017 respectively. Indeed, we even discussed the basic workings of Freeman Dyson's eternal intelligence concept there. In episodes since, we've discussed methods of postponing the heat death of the universe, and alternative theoretical fates to heat death, like the Big Rip or Big Crunch. The latter even has a mirror image approach to Dyson's eternal intelligence, Tipler's Omega Point cosmology, that similarly might permit an escape from entropy. We've looked at ghost universes let go from cyclic cosmologies, dying stars, the end of Earth, and even the last planet. Most recently, though, we were looking at post-stellar civilizations trying to survive in the period known as the Degenerate Era, on stellar remnants like white dwarfs and neutron stars, while they awaited the distant black hole era. And this includes a worrisome gap, because somewhere between the period where natural black holes can be formed and when those other stellar remnants disappear, not only do we have a long time gap, we also have the possibility that all protons, the most fundamental building blocks of atoms, may have ceased to exist by then. So today we will also discuss surviving in a universe in which protons decay. But before we get to any of that, we need to talk about timelines, and logarithmic ones at that. Our universe is staggeringly old and is divided into many different epochs, each very significant, and some much shorter than even a second. So too, our universe is huge and growing bigger all the time, and nothing is really helped by saying that the moon is just over 1 billion feet from you and me, that Pluto is 25 trillion feet away, or that a trip to Alpha Centauri is 135 quadrillion feet. The Andromeda Galaxy is 8 sextillion feet away, or that the current observable universe has a diameter of almost 3 septillion feet. These numbers just don't mean anything to us, and it recalls a favorite comment of mine from Richard Feynman that one of my own mentors quoted us in his astrophysics class: "The sun is much, much bigger than even an elephant." Because our minds simply are not wired to these kinds of scales of space and time that the cosmos present us with. At a certain point, huge is simply huge. Our theory today comes from Freeman Dyson, to whom Richard Feynman was a mentor too, so it's probably no surprise how often his own work featured truly massive concepts and structures, perhaps the best known of which is the Dyson sphere. We spend a lot of time on this channel discussing mega engineering projects like Dyson spheres, and indeed our original episode on this channel, the Mega Structure Summary from way back in 2014, introduced a few different scales for trying to contemplate and categorize these, besides the better known but not really ideal Kardashev scale. We included options for physical size, possible population, energy use, and so on. Like most first episodes, it left a lot to be desired, and I've avoided introducing scales since then, but I think it will help us a bit for today. So we will introduce the T-scale, and as a simple exponential scale for time in years. T0 would be 1 year, T1 10 years, T9 would be 10 to the 9 years or a billion, T12 a trillion, and T100 would be a Google years, 10 to the 100, and this is about how long we think it would take to get to the first dark era of the universe, when the last supermassive black hole of around 100 billion solar masses would finally evaporate. If I just said that proton decay might begin around T34 and stellar mass black holes would begin evaporating around T67, our minds would be tempted to think you could divide this time into 3 equal chunks, as 34 and 67 are about a third and 2/3 of 100. But it isn't so. The time from T67 to T100 is a billion, trillion times longer than from T34 to T67, and T67 itself is 10 million years. T34 by itself is a period of time a trillion times longer than the universe has been around, and we would currently be in the T10 era. The first stars probably arose around the T7 or T8 era. Cosmic microwave background radiation is the T5 era, and ended the photon epoch of the universe, during which there were more particle collisions and events than the entire subsequent billions of years, and whose remnants will still be kicking around all the way into that dark era after T100. So too, we have several epochs of our universe that took place in less than a single year. Those epochs didn't last long, and in order after the Big Bang were the Planck epoch, T-50, the Grand Unification epoch, T-43, the Inflationary epoch, till perhaps T-39, then the Electroweak epoch, running till T-19, and the Quark epoch, till T-13, which itself ended just 1 microsecond after the Big Bang, and lasted an eternity compared to the previous 4. This is when protons first appeared, T-13, and they should last until at least T-34. You will often see those early epochs given in units of seconds rather than years, so for clarification, a second is in the T-7 scale, which is from 0.32 seconds to 32 seconds after the Big Bang. The next epoch, the 6th age of the cosmos we've identified, was the Hadron epoch. This is things made of quarks like the proton or neutron or meson, and it lasted just 1 second and would be 1,000,000 times longer than the quark era and 1,000,000,000,000 times longer than the 4 ages before it combined. Then comes the lepton era. Leptons are things like electrons and neutrinos, and would go on from that first second to that first minute. Prior to this era, matter was still so dense that neutrinos tended to interact with other particles. Only as this lepton era draws to a close do we see the proton begin merging or fusing in the nucleosynthesis events that formed virtually every atom around the universe, although virtually none of the atoms on Earth. This was T-5, and very nearly every atom of hydrogen, helium, and lithium formed during this period of a few minutes. Some of the helium in our Sun was made by fusion in the Sun. The overwhelming majority was there when it formed over 4 billion years ago, and had been drifting around for nearly 10 billion years before that. Our Sun appeared late in T9 and will die sometime in T10, and its white dwarf form will persist until becoming a black dwarf sometime around T15, a quadrillion years from now. It's a bit strange to think of our Sun being on its main sequence lifetime of about 10 billion years, spending another billion or so as a subgiant, then a red giant, then spending about 10,000 times as long as a slowly cooling white dwarf about the size of Earth and more than 100,000 times more massive. This is also about the time we would expect the last stars to die, but we think stellar formation will go on more or less at the modern pace till a couple trillion years from now, the T12 era, and slump off till T14, when we think star formation should finally peter out. and this takes us into the degenerate era. This isn't a time of zero light though. For instance, if Earth was still intact, by gravitational radiation, it would slowly spiral just a little closer to that dead sun of ours till crashing in circa T20, 10 billion times further in the future than the universe is old. When it did, that would reignite things for a while. Jupiter would fall in later, and its vast supply of hydrogen would also reignite that dead sun for a bit. There are also a lot of brown dwarfs and binary remnants lying around still. From T23 to T30, this is what is happening. Binary white dwarfs or neutron stars, both long since cooled, will fall into each other. As we reach T30, all that is left in the galaxy is those cooled and isolated remnants of neutron stars and white dwarfs, and black holes, slowly merging and from a practical perspective still not decaying themselves. Black hole evaporation is just very slow. This whole insane time length is less than a trillionth of a trillionth of a trillionth of the time till black hole evaporation begins. Once they begin evaporating in earnest, we have an immense power source we'll be able to tap, but it's a long way off still. It's also only a 10,000th the time to the bottom estimate for proton half-life, which we'll tease again but return to later, as I think it's time we get to explaining eternal intelligence. I want to emphasize though that this concept works well on paper with no new science required. The difficulty just comes in trying to tap ever smaller amounts of energy and trying to maintain your machinery for it on timescales so long that the basic building blocks of matter those machines are made out of may themselves cease to exist. This is the daunting scale involved, as if we imagined a machine made out of an entire galaxy, one so immensely efficient that only about one atom a month was lost to some sort of wear and tear or decay, just one atom, that it would just barely survive to the beginning of the black hole era at about T67, because there are only around 10 to the 68 atoms in our whole galaxy. But we were getting ahead of ourselves, because our journey begins back in the T10 and T11 era. Over the course of the next 10 billion years or so, we should assume that if interstellar space travel can be made even a little bit practical, that every planet and star in our galaxy, indeed our supercluster, would be colonized by humanity, or some divergent splinter or creation of ours. This assumes no other aliens have already claimed those places, and we might assume that even if we were the first species to develop in the whole universe, that within 10 to 100 billion years, it should have arisen everywhere, and that every star has been claimed by someone, whether they originated from Earth or some older or younger alien homeworld. Today's discussion is taking us to the end of time itself, exploring the concept of eternal intelligence and the ultimate destiny of civilizations. But before civilizations can last forever, they need to survive their beginnings. This month we explore how atmospheres act as a crucial filter for life and its long-term survival on my new Fermi Paradox video, Air. Fermi Paradox Air is now streaming on Nebula, where all SFI episodes air early and ad-free. Nebula is the largest creator-owned platform and home to exclusive content from countless amazing creators. While you're there, check out Faithless, a Sojourn story. This exclusive audio drama follows Cassie and Vadric's perilous journey through the Sanctum. The Sojourn stories are set in a distant future in the Tantalus cluster in the intergalactic void, where humanity finds itself without allies or resources and barely holding on. It's a captivating addition to Nebula's library of premium sci-fi content. Sign up at go.nebula.tv/IsaacArthur using my code IsaacArthur to get 40% off an annual membership. It's less than $3 a month, and you'll be directly supporting this show. Nebula also offers lifetime memberships and gift cards, so you can share awesome content like Faithless and SFA's monthly exclusive episode, available at go.nebula.tv/IsaacArthur. And now, back to our show. By 100 billion years, other than those galaxies closest to us, a dozen or so, every other galaxy will have drifted away from us over the cosmological event horizon, moving away from us faster than light can reach us from them. Every little cluster of galaxies is now its own island, slowly merging into a conglomerate galaxy, which in truth our Milky Way already is. surrounded by more than 100 billion light-years of mostly empty void. We've contemplated extreme galactic scale engineering that might let us save thousands or even tens of thousands of galaxies, and this is a very legitimate thought because once you've been colonizing space for a long time, even just a million years, you've probably settled your whole galaxy, meaning trillions of planets and probably far more megastructures. Whether occupied by people like you or me, or some super-evolved post-humans or AI, they should be accomplishing more units of scientific research in a single second than we have in our whole history and have been at it for a million years. Odds are good if there are ways around entropy or light speed, or tricks for traveling to younger or more valuable realities, they have found it, and if not, they have billions more years to try. But it would seem likely that if they haven't figured out the cheat codes for the universe by then, they will try to figure out how to most efficiently keep things going for as long as possible with a finite amount of resources. This might be with the intent of maximizing research time, or they might have decided that it's futile and they simply want to enjoy their quasi-retirement for as long as possible. Probably a lot of folks and factions doing both, neither, or points in between. In reality, this is the period where stars probably go dark, in T10 to T12, not later at T14, because you probably are surrounding all your stars in Dyson spheres to catch all their energy, and you probably aren't letting new stars form, in favor of capturing their matter for use in your own power plants or trickle feeding to stars you've optimized. As we noted in dying stars, it is possible to harvest helium and other elements heavier than hydrogen from stars, especially the smaller mass fully convective ones that bubble all their material around, even from their core, and remove the buildup of heavy elements that kill them. This allows even stars like our own to be able to live trillions or even quadrillions of years by feeding them new matter and harvesting the heavier elements to build things out of. Though you might need to occasionally yank most of that star's matter off for a good cleaning, thus a star system might tend to keep a few stars going at a time so they could repair and regenerate one thoroughly occasionally. This is a bunkered and cached civilization. No dystopian reality is implied here. They have vast resources and probably nigh-immortal lifespans, so whether or not it's a utopia or some paranoid machine minds sitting like dragons on their personal resource hoards is more reflective of their character than the laws of physics. But everything is accounted for and was either classified as too much effort to grab or has been grabbed and stowed for future use. Those finite stockpiles can buy you so much life. How much depends on your technology and lifestyle, and how big a population you want at any given time. That lifestyle is probably post-human minds living on digital substrates, but never mind that. Your substrate, be it neuron or silicon wafer or paper, probably does matter to your core makeup and mind, but probably isn't the totality of it. Shakespeare is still Shakespeare, whether it's written on old parchment, stored on a flash drive, or printed on a t-shirt or poster, or carved into an asteroid somewhere for posterity's sake. Needless to say, your mileage may vary, and we don't really have enough information to know yet. We don't really understand consciousness, let alone its limitations, but odds are good that if they can be understood by mortal minds, or even post-mortal minds, then by the end of our stellar era, they figured it out. If not, it gives them something to think on as the stars wink out. This is where the dubiously named heat death of the universe comes in. The name is right. Heat is not the same as temperature. It is the type of energy we get when particles are moving around randomly, and you can measure how fast they are moving around as temperature. But a bucket of ice has more heat energy in it than a cup of warm water. So too, space is not very cold, and indeed the areas on the dark edge of the galaxy are often around 1,000,000 degrees. But there's very little matter there, so very little heat, just high temperature. When the universe began, there was a very high temperature, but not much heat compared to now, relatively speaking anyway. Those pivotal first nanosecond-long epochs of the universe were generating more entropy per instant than nowadays, and as the system turns from other types of energy into heat, the entropy of the system rises. It's generally felt there is no way to get around this, that entropy never decreases, only increases with time. The percentage of energy in the universe, which by Einstein's E=mc² includes matter, is shifting slowly but steadily from those other types of energy to heat energy, and will presumably one day reach 100%, barring some tech or phenomena that violates the laws of thermodynamics. This moment is the heat death of the universe, and it's a long way off. Indeed, the rate at which entropy increases may always be positive, but will decrease over time, trending to zero, and a lot of our entropy got generated in that primordial era long before stars even formed. But the temperature goes down. The percentage of energy that is heat rather than mass or potential energy or any of the others rises, but temperature falls. The universe expands and cools, much like any gas in expanding volume under the normal gas laws of chemistry. Everything runs down, and there is no such thing as a free lunch, no perpetual motion machines. Things end in a freezing cold and empty heat death. Dyson's eternal intelligence hypothesis proposes a way for intelligent life to survive indefinitely, even as the universe heads toward an increasingly cold and sparse heat death. In this scenario, where all the stars eventually burn out and energy becomes scarce, Dyson speculated that intelligent beings, or civilizations, might adapt to use energy ever more efficiently, finding ways to extend their thinking and existence indefinitely, albeit at a slower and slower pace. How? Freeman Dyson proposed the concept of eternal intelligence in 1979 in his paper titled Time Without End: Physics and Biology in an Open Universe, published in the Reviews of Modern Physics. A generation earlier, Rolf Landauer proposed what's now called the Landauer limit, the idea that computers, or any similar machines for crunching numbers or processing or thinking, have their maximum efficiency controlled by their temperature. The lower it goes, the more efficient it becomes. Half the temperature, twice the efficiency for the same energy input. 1,000th the temperature, 1,000 times the calculation for the same energy. So if you have a finite stockpile of resources that you plan to translate into a calculator or thought, or virtual environment, it behooves you to do this where it is the coldest, or when it is the coldest. And this is the basis for Fermi paradox solutions like the estivation hypothesis, where we assume civilizations go digital and migrate to the cold extragalactic regions with resource stockpiles they will hibernate near till the cold times come. This is not a very good Fermi paradox solution by itself, since it implies they left to hibernate and didn't bother taking most of the matter in their galaxy with them. And no, it's not dark matter, which is plentiful beyond the galaxy's edge, because we can see back in time and there was just as much dark matter when the universe was barely 1 billion years old as now, so not likely to be secretly composed of ancient civilizations. The universe was way hotter then too. Indeed, at the end of the photon era, the universe was about the temperature of your typical star's surface and closer to that in density too. It's a little under 3 Kelvin these days, about 100th the temperature here on Earth. It will be down to a single Kelvin in around 100 billion years, when star formation is still in its prime, but when we are down to just those large conglomerate galaxies surrounded by 100 billion light years of void. Those are napkin calculations, so grain of salt, please. And anyone calculating out there on the fringe of the merged galaxy ought to get about 3 times more bang for their computing buck than if they did that now, and 300 times more than if they were doing that on modern Earth. By about 1 trillion years in, should be getting down to the millikelvin scale, depending on how we calculate it, and star formation is just beginning to trickle off. Mind you, it's not that cold near these stars, and indeed to obtain these temperatures you probably need to get a good distance from the galaxy. As those stars all die off, we drop below the millikelvin scale, where a computer should now be about 1 million times more efficient than now, at least as a theoretical maximum. The universe presumably keeps expanding, and as the universe cools and energy becomes harder to obtain, people, or beings, would reduce their energy usage by thinking intermittently, with longer and longer pauses between periods of activity. By taking these pauses, they will consume less energy and preserve it for essential cognitive tasks, allowing intelligence to stretch into the far future. So let's say you have 1,000,000 units of energy left. In the first period of time, you use half of them. This is done while you drop from, say, 1000 microkelvin to 500 microkelvin, half the temperature, and you have half your energy left, 500,000 energy units. This translates into some amount of thought and experience. We usually assume digital minds living in virtual realities, say 1,000 years of subjective life. Whatever rate you're thinking is how much subjective life you experience, whether you did that same amount of thinking over 1 second or 1,000,000,000 years. You decide you will spend half of your remaining energy in the interval while the universe cools to half the temperature again. 250,000 energy units, but because it is half temperature, you get twice the thought from each energy unit. The same thought or subjective life as before, so as interval 2 ends, however long that's been, the temperature is a quarter what it was before, at the start, and your energy stockpile is down to a quarter too. You have lived another millennium though, 2,000 years subjectively in total. Next interval, half your remaining supply of energy is used, while the universe cools to half its temperature again. Another millennium of life, and we are down to 1/8 the temperature and 1/8 the stockpile. At the end of the fourth interval, those are down to 1/16, and you've reached 4,000, and so on. In practice, we're not talking thousands of subjective years either, but more like quadrillions. But you could be dividing it up however you wished, maybe one lone megamind that thinks very fast subjectively, or a handful of normal human minds each living quintillions of years, or quintillions of people living each many thousands. And even here I'm really lowballing the numbers, and probably by a dozen orders of magnitude or more. And you can keep cutting in half, each time expending half your stockpile of energy to keep thinking while the temperature cools. This also assumes energy for maintaining virtual environments and repairing equipment though. As time stretches and the rate of thought slows, these beings would perceive their existence in a way that feels continuous, even though from an external perspective, their thinking process might occur at extremely long intervals. This way, an endless sequence of thoughts could still unfold, just more slowly. Dyson suggested that intelligence doesn't necessarily need a constant flow of energy to operate, only enough to sustain thought processes periodically. By adapting their metabolism, so to speak, these beings could continue indefinitely, consuming ever-diminishing amounts of energy per thought over time. This is Dyson's eternal intelligence. Because as the universe keeps cooling and expanding, you keep getting more efficient, and thus never run out of energy or life. You keep doing this all the way to the end of time. Your civilization is eternal, and runs through the degenerate era and on to the black hole era, sucking life from slowly evaporating black holes, from T67 to T100, then into the dark era till the ion stars begin forming around T1500, and after that period into the second dark era, and on and on. Civilizations lasting until the end of time, and the inspiration for the series and those first 2 episodes, black hole forming and ion stars, that chronicle those periods and how they operate, as it is not likely to be a smooth process of continual halving. Now, needless to say, this idea has limitations. Dyson originally assumed the universe would expand and cool forever, providing infinite time and diminishing temperature, but more recent cosmological theories suggest that accelerating expansion in the universe might lead to conditions like the Big Rip or quantum vacuum decay, and we looked at the Big Rip scenario, and maybe we'll do quantum vacuum decay in more detail in the future too, though we've discussed the basic physics as a possible source of energy elsewhere. If you're thinking that tapping vacuum energy gets you out of the heat death scenario, well, maybe, but there's as much reason to think that even if you could tap that, it would drain out too, eventually, albeit it might buy you vastly more time. A Big Rip does offer a parallel escape method to eternal intelligence, much as Tipler's Big Crunch or Megapoint scenario does, though in both we instead reverse our process, using rising energy densities to ever more rapidly calculate, getting twice as much done in half the time. All three of those scenarios, Eternal Intelligence, Big Rip, and Big Crunch, probably have a real limitation on the Planck scale. We generally hold in physics that you can't get smaller than a Planck length, or shorter than a Planck time, or higher than a Planck temperature. Those are respectively about 10 to the negative 35 meters, 10 to the negative 43 seconds, or 10 to the negative 50 years, thus our T50 era, the Planck epoch right after the Big Bang, and about 10 to the 32 Kelvin, the Planck temperature, and the presumed temperature at the moment after the Big Bang. If you want to view those as halving intervals rather than units of 10, generally 10 halves is roughly a thousandth, so to go in half steps up to Planck temperature from room temperature would be about 100 doubling intervals, which is a lot but not infinity, obviously. So too, you have problems running machineries at temperatures so hot they rip fundamental particles apart. Much as it gets very dubious, you could run a machine so efficiently that it could not even lose an atom a century to wear and tear, which is the kind of efficiency needed to operate deep into the black hole era, even when building your machines out of mini galaxies. I have no idea how you would keep a machine working that long, given your limited stockpiles, when we're often talking about timelines longer in years than there are atoms in the whole universe. This doesn't mean it doesn't work to prolong civilizations, just that it probably has its limits. And we should keep in mind that wear and tear and damage don't just happen for no reason. In an ultra-cold, slow, and low-energy environment, there really are not many things causing wear and tear, so it is entirely plausible you might have very slow loss and damage rates. That this could be atoms a year on galaxy-sized constructs does seem a bit much though. And it is not a subjectively short epoch either. A civilization that saves matter up for the post-stellar era might experience not just slow eons of stretched out existence, but subjective time spans of their civilization vastly longer than trillions of years. As we said in black hole farming, it's only dark in a relative sense. They would view their stellar era time as this tiny, energetic fraction of the universe that was brilliant, but short to them the same way we view the Big Bang itself. We, to them, are a civilization somehow existing in a rapid explosion. But we have some other limits, and those can include options like a power source that simply cannot operate below a certain threshold. You are not extending your civilization much if your fusion reactors cannot generate below the megawatt scale, for instance, or cannot do it efficiently. You might be flipping on for an hour once every quadrillion years or something. It's easier to explain the concept of Dyson's eternal intelligence as a smooth timeline, where each stretch takes half as much energy and produces twice as much thought for each mode of energy. But in practice, what we're really suggesting is probably an intermittent civilization, one that goes into near-complete hibernation between firing up their reactor again, during which time their circuits cool. Those circuits have to be at those ultra-low temperatures to take advantage of that ultra-cold efficiency, and it takes a very long time to cool down to that next lower temperature, so huge times must pass between firing a circuit too. When the circuits cool down to that new base temperature, which is lower each time and takes longer to reach each time, they fire their circuits again to create calculation or thought, or run their subverse they dwell in. Or alternatively, they fire up their civilization as each new black hole in their stockpile, each just a bit more massive than the last, reaches that point where it produces usable levels of power after a long period of ultra-slow evaporation. Black holes produce vastly more power when they are lower mass. The relation is inverse square, so 1/10 the mass, 100 times the power output. I should note that an intermittent civilization, especially in this way, where each thought has a long pause between it, might run into some identity and consciousness issues. We don't really understand either of those, but one of the more common philosophical notions of identity, coming from John Locke, is that it requires continuity, no sudden changes, and maybe no ultra-long pauses. Though we take for granted that sleep maintains identity, we don't wake a new person each day. But civilizations might get philosophically uncomfortable about quadrillion-year pauses between words in a conversation. Indeed, for all that black holes have immense lifespans, it is worth noting that if every drop of matter was put into black holes of various sizes to stagger them out over the black hole era, there would not be enough mass in the whole known universe to let them run with one at a time, perpetually producing even a single watt of power, because the mass energy of the whole universe is just shy of 10 to the 70 joules. Which means even if you're only trying to operate to T70, not T100, you only get to have 1 joule a year, about 30 nanowatts of power. Of course, if you're operating at the nanokelvin temperature, and indeed a lot lower by then, that would let you run quite a few mines and at a real-time speed. Again, the numbers are just so staggering that they cannot be intuitive, and we saw them in more detail in those earlier episodes on black hole farming and iron stars. But to get to those eras, you have to survive the degenerate era, and that's not necessarily an appropriate name just because the few celestial bodies remaining are dead stars made of degenerate matter, or even that all orbits are slowly degenerating to cause things to fall together. We do not know that any particles are completely stable, meaning have half-lives. Indeed, from a certain perspective, most particles have half-lives so short they could not make a trip at light speed outside their own atomic nuclei, as we discussed in our episode Antimatter Factories. We only see those few types that can, but a lot of things are stable, and we think the electron and photon, for instance, are both totally stable. We think the neutrino is as well, and probably the graviton if it exists, but protons are made of quarks and gluons and may have a half-life. Neutrons do, they last mere minutes by themselves. We do not know if the proton does decay, but we have reason to think it might, particularly in supersymmetry models, which I should note I am not personally a big fan of, though it is a brilliant and detailed theory, and my opinion probably should not matter. Regardless, we know that if protons do have a half-life, it is not less than 10 to the 34 years. It presumably takes a lot less time than that to determine if protons do decay and how long their half-life, if any, actually is, but everything we normally think of as matter is made out of protons, since they are at the center of every atom, even simple hydrogen that lacks a single neutron in it. And again, neutrons do decay, when in isolation. So do the bigger leptons like the muon and tau particle, but we think the other leptons, electrons and neutrinos, are eternal, and that presumably includes their antiparticles like the positron. So what do protons decay into? Well, we don't know if they decay into anything, so we can't be sure what they would decay into if they did, but we have two main guesses. Option 1. The proton decays into a positron and a neutral pion. That positron presumably lives forever, unless it encounters an electron, in which case they slowly orbit down, attracted by their opposite charge until they touch and typically annihilate as a pair of photons of 511 keV energy each, which is how we discovered positrons and antimatter incidentally. The neutral pion or pi meson is composed of two quarks, one up and one down. There's a positive and negative pion too, made of a pair of up or down quarks, and they only have a half-life of a few nanoseconds, and the neutral pion is even shorter-lived, about a billionth of a nanosecond, so not something you build an eternal empire out of. They turn into a pair of photons, so proton decay this way ends up as photons. If we imagine some hydrogen atom in the deep void, far from a galaxy decaying, the proton decays into a positron, which then collides with the electron the hydrogen atom had and leaves us two photons, which is after the neutral pion has decayed into two photons itself. This might be a decent power source for civilizations trying to carry on into the degenerate era, while their matter runs out from proton decay, and it's amazing how big an energy budget that really is, given what the temperature of the universe would be by then, something south of a trillionth of a Kelvin. Under Landauer's limit, that's way more useful calculation from a single stellar mass than you could get now from Dyson swarming entire superclusters of galaxies. The other decay mode suggested for protons is into a muon, the electron's big brother, and a photon, and that muon will decay into an electron, or rather that positively charged muon left from the positively charged proton it decayed from will decay into a positron, the positively charged antiparticle of the electron. Some suggested decay modes instead result in lighter mesons and neutrinos, but we'll bypass that for now. So, is that it? Just positrons and electrons decaying into each other and creating more photons to join the photons and neutrinos flitting around the universe. Well, photons and gravitons, if they exist, are massless particles, so they experience no time, and thus don't decay over time, while neutrinos might have some mass and thus experience time and might eventually decay too, potentially even faster than protons, as some models predict anywhere as low as 10 to the 20 to 10 to the 30 years as a neutrino's half-life, decaying either into a photon or a majoron. Majorons are a topic for another time. So is dark matter, which you might conceivably be able to build stuff out of, and maybe very long-lasting stuff. We don't want to casually brush off weakly interacting particles like we think dark matter might be made of, given how long the timelines involved for them to interact over might be. Maybe we could build data engines and computers from dark matter. But a positron and an electron do not have to collide. They are attracted by their opposite charges, and at a normal atomic distance we see in hydrogen or other matter, they will fall into each other. We call a positron-electron pair positronium incidentally, and it need not be short-lived. This isn't just random speculation anymore either. We've even made molecules out of it, short-lived though those were. Imagine a positron and electron floating far apart in space, far from other matter and orbiting very slowly. This will decay with time, but you could build thinly spread devices out of positronium perhaps. Indeed, imagine for the moment that you spaced a positron and an electron just far enough apart that the force of their attractive charge was exactly balanced by the push of dark energy seeking to separate them. They might remain forever locked at that distance. Very hard to do, possibly impossible, but if proton decay is real, people have about a trillion years to figure out how to make machines and computers out of positronium instead of regular matter, or to create micro black holes or sip at vacuum energy. If it is possible, that is a lot of time to figure it out. And that's what it comes down to in the end. If there's a way to make Dyson's eternal intelligence practical, to reach out for that tantalizing possibility that intelligence might adapt and survive eternally by slowing down in harmony with the universe's cooling, to use ever more efficient energy conservation methods, to exist at the universe's farthest reaches of time, then we have all the time to figure out how to either do it or to find some other alternative, to escape to some other place, some younger universe, or one where different rules apply. So perhaps civilizations will persist until the end of time.